Okay guys, in the previous class, part 16, we were talking about the rank deficiency of Jacobian metrics, or generally any metrics, that's right. And I said that Jacobian is 6 by n, and then it's number of degree of freedom or joints. So if n is smaller than 6, so if you want to make sure that if you want to have the inverse of this matrix, because of what? Because of our famous relation, that's right, x dot and the vector velocity is Jacobian in the end of the links, joints angular velocities. So because I told you in the backward inverse kinematics, we're going to have theta dot is equal to j minus 1 in x dot. But when n is smaller than 6, so this is not possible. So I taught you about the what? Pseudo inverse. But when n is smaller than 6, and we started this definition that if matrix A, or any matrix, this is generally speaking, has linearly, remember from the previous class, linearly independent columns, meaning that rank of the matrix A, rank of A, as I did in MATLAB, I'm going to do again today because I'm going to complete, is equal to number of its columns. That's right, its columns. That's right. So we have pseudo inverse as left pseudo inverse, left p in. Remember, in the this is MATLAB command. P in is equal to A transpose in A inverse in A transpose. That's right. So if you, when you n, okay, number of the column are smaller than the number of the rows, okay, so if you say A plus or pseudo inverse, left pseudo inverse in A, gonna be I. But what kind of I? Because A is suppose A is n by 6. Oh, sorry, 6 by n. But pseudo inverse gonna be left pseudo inverse gonna be n by 6. So I, the identity matrix, gonna be n by n. Okay, as we did in the MATLAB in the previous class. For the left pseudo inverse. For refreshing your mind, let me go to the MATLAB in the previous class. Can I? Yes, I can. So here we go. Hold on, it's going up. Okay, so remember that for the 3 degree of freedom robot that I solved in detail in Jacobian Matrix in the class you have in notes, suppose that Jacobian Matrix J is as I told you, because when you have 3 degree of freedom system, guys, let me write it down here. Again, when you have 3 degree of freedom system, as I solved in the class in detail, your Jacobian matrix is gonna be 6 by 3. That's right. 6 rows and 3 columns. Go and take it. Suppose for a certain time The J is 1 2 3 minus 9 5 4 0 0 1 0 2 minus 30. 1 2 3 4 5 is 5 500, and the last one is 0 100 0 3.5. Here we go. This is how much? This is 1 1 2 3 4 5 6 and 3. So this is for, suppose that 3D graph freedom robot that I solved in the class for Jacobian Matrix. So as I said in the previous class, it says left pseudo inverse gonna be calculated as inverse of, as I just said, J transpose, that's right, multiplied by J, that's right, as I wrote here. So it's inverse of this multiplied by J transpose. And I taught you that if you write like this as a left pseudo inverse, this is 6 by 3, it's going to be 3 by 6. See here? 3 rows and 6 columns. So obviously, if you multiply LP multiplied left pseudo inverse in the Jacobian, that's right, this is pseudo inverse of Jacobian, gonna be 3 by 3, as I told you, identity matrix 1 1 1. Remember? So when you have the rank deficiency, another point that I said, the rank of the Jacobian, because you have 3 columns here, 1 2 3, so its columns are linearly independent, that's right. But okay. So rank of the Jacobian here is 3, because you have 3. So now we go to left pseudo inverse. Now let me go to the case that I do have in my lab. In my lab, I have Baxter, okay, which we name it as redundant robot. So Baxter, that we published many research articles on that, has 7 degrees of freedom in 3D space. Okay, here we go. If I go to my lab website, payman.nm.sdsu.edu. Okay, this is my lab website, and you see that this is the let me, okay, this is the Baxter, that's right. This arm, you see that this arm each has 7 degrees of freedom. This is 1 and 2 3 4 5 6 7. Okay, so it had 2 hands, each 7 degrees of freedom, so totally has 14 degrees of freedom, and has camera inside for deep learning that we have trained the camera to detect the object, avoid the obstacle, and put the object on the obstacle. So anyway, now we are on the topic of the Jacobians, right? So by having this, so because I have 7 joints, so Jacobian gonna be 6 by 7. Now the number of the rows is less than columns, so n, which is 7, is greater than 6. In the previous case was smaller than 6. So here we name Baxter has 1 degree of redundancy. If you have a 8 degree of freedom robot that we do have in the lab, I have a 18 degree of freedom, that's right, like as a rescue robot. So its n is 8. So here I have how many degree of redundancy? 2, because 8 minus 6 is 2. If you have 15 degree of freedom robot, so it's gonna be it's gonna be 7 degree of redundancy, because 15 minus 6, oh, I'm getting all the guys, gonna be 9 degree of redundancy. Redundancy is good because it gives you dexterity and to avoid the obstacle on the space. At the same time, it complicates the computational burden when you want to control the robot guys, okay? Because you have lots of joints, so you have the interconnection between them. When you design a controller, eventually you're going to have the computational inefficiency sometimes. Sometimes this added degree of freedom causes the time delay in establishing the system if that the sampling rate of the robot, like the Baxter that we have in the lab. So the sampling rate of the Baxter in the base scenario is 100 hertz. So the best, if I'm not wrong, the sampling rate of Baxter in the best scenario is 1000 hertz. Okay, 1000 hertz. Okay, so if your calculation at each iteration is not within this time, okay, you're gonna have time delay. So it's gonna be an unstable system. We published too many papers. Please go to see my lab. Okay, so now let's back to the Jacobian. Okay, the Jacobian of the Baxter. So in this case, I have to introduce new concept, which is if a general matrix has linearly independent rows means rank of matrix is equal to number of rows. Okay, so you're gonna have you have to have right pseudo inverse. How we calculate that? So right pseudo inverse, let me double check here because I said number of matrix. Right pseudo inverse is like this: A transpose inverse, and that's it. This is right pseudo inverse when you have a degree of redundancy for the robot manipulator. Okay, so if I want to summarize in one page at the end, so let me change the color. For left pseudo inverse, left p inv, so it's gonna be pseudo inverse gonna be A transpose A inverse A transpose, but right p inv MATLAB code that you're gonna see. So you're gonna have A transpose gonna be A transpose. I'm moving this way. That's right. In A transpose inverse. So you just compare this with this one. So that's it, right? So now let me go to MATLAB for the right pseudo inverse. Suppose I have to generate. Hold on, I generated numbers. I don't want to go. I can do that actually. Suppose you let me first. Suppose in a certain time, okay, Jacobian matrix of the Baxter I have in the lab is like this, okay. So 6 by 7. So gonna be 1, 2.5, 22, 3 minus 4, and 10. This is first row. So it's 6 by 7, that's right. Now this is gonna be 1.4 minus 3, 3.5, 2.2, 45, 4, and 0.2 second row. Now I'm gonna say 101 plus 33, 35 minus 44, 0, 1, 1, 2, 3, 4, 5, 6, 7, and 20. Third, okay, fourth row gonna be 30.5, 3.3 minus 1, 0, 0, 1, and 0. And now fifth, that's right, gonna be 22, 1.7, 9.4, I don't know, minus 2, minus 1, minus 11, and 21. And the sixth line, that's gonna be 33, 43, 65, 77, 88, 99, and 0.1. Here we go. So suppose for a certain amount of time, suppose that t is equal to, I don't know, 0.0 seconds. This is Jacobian Matrix of the Baxter Hamilton lab, and we have done, we have done lots of experiments. Had 1, 2, 3, 4, 5, 6, but 1, 2, 3, 4, 5, 6, 7 what? Columns. First of all, I have to check the rank of this matrix. I want to make sure that the rows of this matrix has linearity. Yes, it is, because rank of this matrix is equal to the rows of the rows of this Jacobian matrix. So you see that for the redundancy that I have more freedom than the space coordinates, it's important that you double check that the rank of the matrix is equal to the number of the rows. It's full rank, on the other hand, as control wise speaking. So then, now if I want to say write pseudo inverse based on what I write out, gonna be J transpose. Look at here. Here we go. J transpose, this formula, J transpose multiplied by inverse of J multiplied by J transpose. Here we go. It was 6 by 7. Now it's gonna be 7 by 6. That's right. 1, 2, 3, 4, 5, 6, 7. So now let me go back to the notes, because I go one by one for the Baxter. So suppose for the Baxter that the J is 6 by 7. So you have to multiply by pseudo inverse, right pseudo inverse. You are multiplying from the right. Remember, here we are multiplying by, here we go, from the left we were multiplying, here we are multiplying from the right. Then this is 6 by 7, and this is gonna be 7 by 6, as you saw. So the result gonna be identity matrix must be, because this is kind of inverse, right? 6 by 6. That's right. See, 6 by 6. This is matrix rules. That's right. So if I say now right, that's right. So you have to say J from right. You have to multiply by the right pseudo inverse. Obviously gonna be 6 by 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 1, 1, 1, 1, 1. There is no exception, guys. So you as robotic engineer, you have to judge about this very, very carefully. You have degree of redundancy, or you have what? You have the joints lower than 6 in 3D space. You have to know where to use the Jacobian matrix. Left pseudo inverse or right pseudo inverse. This is very critical, guys. Very critical. I'm emphasizing it several times. If you blind your eyes and just want to solve a robotic problem, you are done. These are trivial things that you have to know. But as I taught you in the previous class, let me, this is your 6 for the Baxter for say. So it is not so as simple as this: J multiply by P inv of J, because in the previous case we were multiplying P inv, so the inverse from the left, but for the Baxter that has 7 degrees of freedom, we are gonna be 6 by 6. You don't need to use this formula by hand. You don't need. Okay, this is for teaching only purposes. If you from the right you multiply by P inv, you are fine. Understand? Now let me go say that you have 8 degrees of freedom. So I'm just adding one elements here. 12, 2.2, 0, 1, and 22. Here we go. So this shows this Jacobian that you have 8 degrees of freedom robotic system in your company, in your lab. So because it's 6, 1, 2, 3, 4, 5, 6, 7, 8. So what you're gonna do, you're gonna say you have to use right pseudo inverse, because 8 is greater than 6. So you're gonna have J multiplied by P inv of J. The result gonna be again 6 by 6 identity matrix. You understood? Great. Okay, so we can do too many things, but let me go to a little mathematics. Is recording? Yes. So guys, let's math a little. Okay, so for J with Jacobian matrix is a member of Rm by n, means that m rows and n columns, and this is I'm talking about, guys, I'm talking about right pseudo inverse, right pseudo inverse. Okay, and m smaller than n, right? Generally speaking, like a 6 smaller than 7. So this is for redundant robots. I'm talking about, let me write here, I'm talking about redundant robots. Redundant robots. And then J Jacobian matrix in J transpose inverse exists. Okay, exists, as I taught you, because if you have J is, for example, is 6 by 7, and J transpose gonna be how much? How much gonna be from mathematics? Yes, 7 by 6. Sorry. So from here you know that J in J transpose gonna be how much? 6 by 6. 6 by 6. So having these conditions, okay, J transpose, because see, if this is M, if this is N, like here, see, MN, so this is gonna be NM. So the result of JD transpose is gonna be M by M. This is a matrix operation from high school. Member of subset of M by M has a rank of M. Has a rank of M, as you saw in the MATLAB, has a rank of M. Understand? as the rank of n. So now let us go and develop this. There we go. Okay, so now we established that J transpose exists, right? So, and we have inverse of that. Okay, now look at here. Based on this, if this is a matrix, whatever we say is B, okay, so we know that B in B inverse is always is equal to I. We are using the same concept. J in J transpose in J transpose inverse gonna be what? I, identity matrix. We know this from mathematics. Now you can rewrite this, guys. Okay, you can rewrite this. You can say J in J transpose in J transpose inverse is equal to I. Yes or no? I just separated this. So have you seen this? Yes, you have seen it. That's the right pseudo inverse. That's right. A transpose, we got here J transpose. A J transpose A transpose and inverse. So now I'm gonna say right pseudo inverse. Okay, so here this is gonna be right pseudo inverse, okay, of J. Obviously we know that J is Jacobian matrix in J right through pseudo inverse for redundant robots is I, identity matrix. Understand? So 4, but don't forget that for redundant robots, this is valid. But what about this? J's pseudo inverse in J is I? No, because this is left pseudo inverse that we saw that for number of degree of freedom is less than 6 in 3D space. So be very careful, guys. Again, be very careful. Okay. That's it. Hold on. Done with the basic concept of the pseudo inverse in the robotics. So, but the next things that is not in the syllabus, but I would like to have a review for you, is computer vision and deep learning. Computer vision and deep learning. Okay, so guys, I don't want to go into detail of that because it's too much for you, and but I just want to show this experiment that we have done in the lab. This is because this is a research work. This is not undergraduate or between graduate and undergraduate teaching topics. You see that we have the bags in the lab. So based on the orientation, so we tilted the object, as you can see here. By learning the camera of this Baxter, when using deep learning, we can determine the angle that is tilted. Why? Because the end effector must rotate to 31 degrees to grasp the object, and then based on the HSV based scanning, means hue, saturation, and I forgot the last one. So we detect the object based on the by assigning that the red is the object, the blue is the obstacle, and the path, the green is the destination. And then we are using some SP-line curving based on these data, because by stereo vision we are detecting 3D positions of the objects. Let me run it for you and you see it. See, these are the 3D positions with respect to the camera of the Baxter. See, 3D positions. Let me hold it on. Then go back. Then you see that it's learning. It learned, and now the end effector is rotating. Goes and grab the object. Let me pause it. Okay, and based on these 3D positions of all of these items with respect to the camera, we fit a curve to avoid the obstacle, and we have the pick and place task completed. Okay, but this is too much for the robotic class, but I want you to assign a homework for yourself. So because we published this as a conference, Dynamic System and Control conference, by my former master student, and now he's my PhD student, and he's doing great, Alexander Bertino, I'm sorry. And this is the paper that I'm gonna open. Yeah, this is the paper. Experimental autonomous deep learning based 3D path planning for a 7D Grafton Baxter robot. It was me, and it was my current PhD student, Alex Bertino. Mustafa Bagheri was my former PhD student, and my Miroslav Kirtic, my collaborator at UCSD, and this is your glorious professor. So we presented this as ASME 2019 Dynamic System Control Conference at Park City, Utah. So I'm going to share this in the Blackboard. I want that you go through it on the class time of Thursday, just grasp what we are doing in the deep learning simply. Okay? And the paper is written very simple. Okay, you can understand. So Thursday class, I'm just going to skip. I'm going to give you time to read that, and then next week we're back. We go to the dynamics of the robots. Okay.